Okay, so taking a look at our parent function. So first of all, what does parent function even mean? Well, if we take a look at the blurb at the top, it says, these are the most basic forms of the functions you should know about. You will need to know what they look like and at least 3 to 4 points on each. So, basically, you're going to need to be able to graph these pretty quickly. And most of them you know how to do already. And if you don't, after we go through them, hopefully you'll remember. Because we're going to be taking these parent functions and then we'll be transforming them. Sliding them around, changing their slopes, zooming in, zooming out on them, doing all sorts of things. So if you don't know what the original function looks like, it can be kind of hard. All right, so if you're going to graph y equals some constant, any old constant, it doesn't really matter. It's just a horizontal line at whatever that constant is, right? So that would be my value of c. So that one's pretty easy. We are also being asked to find the domain, range, and intervals which the function is increasing, decreasing, constant. Does it have any relative maxes or mins? So I'm actually going to hold off on you doing that because I have you doing that on a separate sheet here. And it's sort of laid out a little bit better. So I'm going to answer that on the next worksheet. Okay? So linear. If I graph y equals x, what does that look like? It has a slope of 1 and it starts at the origin. Yeah, it's just that your perfectly diagonal line right through the middle there. So that is your graph of y equals x. How about a quadratic? We've been talking about these more recently. Yes.
It's like a U that starts at the origin.
It starts at the origin. Now, do you guys know the shortcut? I mentioned it the other day, and I feel like a lot of you were confused. How to find the rest of the dots? Yes, 135. So, if you don't know what I'm talking about, well, let me start here. If you have no idea how to graph something, you can always just plug in numbers. It's helpful if you know, oh, okay, it's an x squared. It should be a parabola, a U shape. That's helpful to know, but even if you don't know, if you just plug in enough values, it's going to come out to look like that anyway. So if I plug in positive 1, 1 squared is 1, right? So if I plug in positive 1, I get out positive 1. Well, what happens when you plug in negative 1? Negative 1 squared is still positive 1. So negative 1 comes out with a positive 1. Notice, to get from this dot to this dot, I went up 1 over 1. But I don't go up 1 over 1 to get to the next dot. Oh, no, no, no. Because if you plug in 2, what comes out? 4. So 2 comma 4 is my next point. If you were to plug in negative 2, positive 4 would still come out. Oh, do you see how it's coming out to be like a U shape? So look, I went up 1, but then I went up 3. Well, that's interesting. Let's do one more. If I plugged in positive 3, I'd get out 9, wouldn't I? Yep, I have to go 1 off. And if I plugged in negative 3, I would get out positive 9 also. So there is my beautiful parabola. But take a look, guys. There's a pattern. I went up 1, I went up 3, I went up 5. I would go up 7 if I had enough room. That's your pattern when, remember in quadratics, ax squared plus bx plus c? Like when you're doing quadratic formula and you have to plug in a, b, and c? If a is 1, that's your pattern. So wherever the vertex is, you just plot the vertex, and then to get all your other points, you just go up 1, 3, 5, and that should be plenty. So you don't have to like do it out every time. So even if I asked you to graph this crazy thing, x squared minus 3x plus 2, who cares? Once you figure out where the vertex is, which this one wouldn't be at 0, 0, you find your vertex, and then you can get all the other points by just, because a is 1, I just go up 1, 3, go up 1, up 3, up 5. So it's a lot faster. As long as a is 1. And when a is not 1, we'll talk about that later. You may or may not remember how to graph this guy, though. The cubic function. Do you remember? Well, if you don't know, just plug some numbers in. Let's plug in 0. What's 0 cubed? 0. So that's a point on my grid, on my graph, 0, 0. If you plug in 1, what's 1 cubed? 1. 1, 1. That's another one. But now, plug in 2. What comes out? 8. 2, 8. That one's all the way up there. If I were to plug in 3, it'd be 27. So that's way off my grid, so I'm not even going to bother. Let's do some negatives, though. If you cube -1, what comes out? What's -1 times -1 times -1? Yeah, so -1, -1 is a point. Try -2. What's -2 times -2 times -2 is? -8. -3 would obviously be -27, and then I'm way off my grid. Everything's crazy. So when you put all this together, it just looks like this. It comes from down below. It does a little woo. It goes like that. So that's what your cubic function looks like. So do you need to memorize this? No, but you need to be able to recreate this just like we did. Right? But I don't memorize them. You could just very easily, okay, I can just cube the numbers real quick. And there they are. So there's my cubic parent function. Okay, now, if you take a look at the back, some of these you may know and some of these you may not know. Absolute value. Do you remember what that one looks like? It's a V shape. Do you remember what the square root one looks like? Yes, half of a sideways parabola is a good way to describe it. That's basically what that guy is. Do you have any idea what this thing even is? Have you seen these symbols before? See how it's like a closed bracket, but they're like double. That's something called the greatest integer function. So what in the world is that? Basically, you're going to what's a good way to describe this? So you want the greatest integer that's going to be less than or equal to the value that you're at. So, for example, if I were to ask you, what's the, if I plugged in 2.3, the greatest integer less than or equal to 2.3 would be 2. What if I asked you to plug in 3.7? What's the greatest integer less than or equal to 3.7? What was it? 3. Yes. So it's not quite the same as rounding, right? Because if I rounded 3.7, you'd usually round it up to 4. You're going to round down to the integer that came before that number. That's less than or equal to your number. So we'll do a couple of these, and then the reciprocal one. Do you know what this one looks like? Well, this guy has a problem to start with because he has a variable in the denominator, right? So he cannot even exist when x is equal to 0. So what happens is we have one of those asymptotes at x equals 0. But anyway, we'll talk about that one. So let's go back to absolute value. This is a V shape. Where does he start? At the origin. Isn't that funny? Most of your parent functions are going to start at the origin. And then if you don't know what it looks like, guys, just plug values in. Plug in 1. What's the absolute value of 1? 1. What's the absolute value of 2? 3. Oh, Miss Sabia, that's just a straight line. Well, you didn't go negative yet. What's the absolute value of -1? +1. So on this side, right, even though I'm plugging in negatives, it's going to spit out positives. That's how you get that V shape. And one of the most common mistakes is that kids will just plug in numbers on this side and just make it a straight line. That's why it's so important to ask yourself before you start, what does this graph look like? You know it's supposed to be a V shape, so don't just connect that side and call it a straight line. That's crazy. But that is a nice V shape, just like what we were expecting. So there is your parent function for the absolute values. Okay, square roots. I can't plug in negative x values here, right? They're not in my domain. The graph does not exist when x is -1, -7, -100. It doesn't exist there. Where does the first place it exists? At the origin. I can plug in 0. That's the smallest thing I'm allowed to plug in. If I go less than 0, it's broken. So when I plug in 0, don't I get out 0? Square root of 0 is 0. Yeah? Yeah. Plug in 1. What's the square root of 1? 1. You can plug in 2 if you want to work harder, not smarter, and that's not my life's motto, so I'm not going to bother plugging in 2. I would not bother plugging in 3, but I would plug in 4 because the square root of 4 is? Yes. It's not that the graph doesn't exist here, it's just that they're weird decimals that I don't know what their exact values are. So I'm not even going to try and guesstimate. Right? It exists, I just don't know them. Do you know the square root of 3? 1.41 something, I think. Or is that 2? I don't remember. See? I don't know, because I don't need to know. I'm not going to plug in 5, or 6, or 7, or 8, but I would plug in 9. What would 9 come out as?
3.
That's it. So these graphs, a square root graph looks like this. Half of a sideways parabola. Okay. Ready for this greatest integer one? This one's weird, but once you get the hang of it, it's not so bad. Alright, so let's try plugging in some values. Maybe that'll help. In fact, I'll make a little table. Okay, we did a few already. I said that the greatest integer is the integer that's less than or equal to the value that you have. So, when I said, what did I say first? I don't know, 2.1. What'd you guys come out with? 2. 3.9. What'd you come out with? 3. How about 1.5? What would that be? 1. Let's go negative. What would negative 1.2 be? Which one is it? What is the integer that's less than or equal to this one? Negative 2. Negative 1's bigger than... Yeah, so careful when you go negative, right? What if I put in a number right on the spot? Like, say I put in, I don't know, what if I put in 2? What's the integer less than or equal to that one? 2. It comes out as itself. So here's how these look, okay? If you plug in 0, you're going to get out 0. So I do have a dot there. If I plug in a half, what do I get out? Oh, sorry. Oh, that's what you were saying. It's on the other side. If I plug in a half, what's the integer less than or equal to a half? 0. So if I plug in a half, I still get out 0. If I plug in positive 1, what would I get out? 1. So basically what this looks like, I'm going to have a perfectly horizontal line from 0 all the way until I get to 1. But then when I actually get to 1, it's going to jump up to 1. And then the same thing happens. 1.5, we said stayed at 1. 1.9 stays at 1. Everybody will stay at 1 until I hit 2. And then at 2, it's going to jump up. And I'm going to keep repeating this process basically all over the place. And it works the same way back here. So these just came from this way. They look like a series of steps. And it just keeps going. I mean, forever. We probably should have changed the scale so we didn't have to draw so many of them. But that is what the greatest integer function looks like. Does that kind of make sense? Okay, there's all of them. And my hand hurts now. So let's just jot in words. The greatest integer less than or equal to x. A good way to think of this is like your age, right? So once you hit 16, you're 16. If you're 16 years old and 1 month, don't you still just say you're 16? Right? If you're 16 and 7 months old, don't you still just say you're 16? You are 16 until the day you hit 17. Then you jump up. Then for that entire year, you're just 17. Technically, you're not, though, right? You're 17 and so many months and days and whatever. But when someone says, how old are you? You just say 17. Does that make sense? So if you think about it that way, that might sort of make more sense. And then you can kind of see how, yeah, we usually just say whatever age we are. We don't normally, unless it's a newborn, you don't talk about the months. But, okay, so there's that one. Then the last one is the reciprocal function. So we already said that we're going to have an asymptote at x equals 0 because I can't have a denominator of 0. So I'm putting a dashed line here, which is not part of my graph. It's just saying my graph doesn't exist here. So I have an asymptote there. Remember that funny spelling, A-S-Y-M-P-T-O-T-E. So, we're assuming we have no idea what this graph looks like. I just know it doesn't exist at when x is equal to 0. All right, let's plug in 1. Because I can't plug in 0. I would always start at 0, but I can't. So let's start at 1. If you plug in 1, what's 1 divided by 1? 1. So when I plug in 1, I get out 1. Okay, cool. There's a dot right there. When you plug in 2, what happens? What do you get out? A half. Interesting. So if I plug in 2, I get out a half. So when I plug in 3, what am I going to get? A third. What's going to happen as I plug in bigger and bigger and bigger x values? Yeah, it gets smaller and smaller and smaller and smaller. But will it ever get to 0? No. And is it ever going to go negative if I'm plugging in positive values? No. So even when I plug in 100, it's just 1/100th. It's just super tiny. But it will never go negative as long as I'm plugging in positive values. So what happens is this guy is going to get infinitely close to the x-axis, but he never actually touches it. I know it's hard to draw, but he's never actually going to touch it. He's just going to get super, super, super close to it. Now, I started at 1. But there are values in between 0 and 1, right? Like a half. What would have happened if I plugged in a half? What's 1 divided by a half? 2, right? If you plug in a half for x, 1 divided by a half. If I'm dividing by a fraction, I really multiply by the reciprocal, right? So it's really 1 times 2. If I plug in a half, I get out 2. Well, that's interesting. What if you had plugged in a third? What would you get out? 3. Oh my gosh. So if a third would be 3. A fourth, I would have gotten 4. What if I plugged in, I don't know, 1/10? I would have gotten out 10. So what's going to happen right here is that this thing is going to get infinitely close to that asymptote, but it'll never actually get there. That's important to think about because a lot of times kids are going to make the mistake and just think that the graph starts at 1. Well, no, it doesn't. It just can't exist at 0, but it can exist at a half, a fifth, 5/9. It can exist there. It just can't exist at 0. So it doesn't start at 1, though. So I have this whole branch. We haven't even plugged in negatives yet, though, so we're not done. What happens when I plug in -1? -1, yeah. So basically, the whole same thing happens. If I plug in -2, I get -1/2. So I'm going to have the same exact thing that happened here happening over here. It's just I'm down in the 3rd quadrant. So the graph again is going to get infinitely close over here and infinitely close over here. So guess what? I have another asymptote. The x-axis is another asymptote. My graph is never going to get there. I'm actually going to I'll outline my asymptotes in orange just so maybe it'll make it a little bit clearer. So my graph, and maybe I'll outline my graph in there we go. Okay, so there's that. What's the domain of this thing? Right. Everything except 0. I can't have 0. I can have everything else. What's the range? Y can't equal 0. But I do get y values for everything else. So that's what your reciprocal function looks like. Okay? Does all this kind of make sense? So here's what I'm going to do now.